Hey everyone. So now we will show that OLS is unbiased in the multivariate case. So we again consider the properties of the OLS estimator in the classic linear regression model where we assumed that the x's were fixed, so the x's were non-stochastic. And the same applies again, we can kind of relax this assumption later on and consider stochastic axes where the x's are actually random variables, but this case will be much easier to deal with, right? So we extend our previous set of assumptions that we had that we need to show that OLS is unbiased to the multivariate case. Okay, so in order to do that, the first assumption is, of course, again the linear model assumption, but now just using the vector representation of the linear model, including, of course, this includes the intercept. The second assumption is that the x's are fixed, as we discussed. So this xn vector is fixed. The third assumption is now a slight deviation from the previous case where we talked about axis or there being variation in the axis. Now this assumption is that xn prime has full rank, and I talked about this already previously, that we needed this assumption in order to actually derive the OLS estimator, right? In order to be able to take the inverse of that xn prime matrix. And then the fourth assumption is the expectation of epsilon n is equal to 0. That's the same as before. Okay. This is kind of what I said in the previous video, that in general, whenever we have a matrix or the rank of a matrix multiplication of the form A prime A that is equal to the rank of the matrix multiplication AA prime, which is equal to the rank of the original matrix A or A prime, which is just the same to say that xn prime having full rank means that the rank of x, the original data matrix, is equal to k, which in other words, and I talked about this in a little bit more detail in the last video, implies that none of the independent variables is a linear combination of the other independent variables, right? So this assumption, xn prime having full rank, implies that there's no perfect correlation between one of the regressors and a set and another regressor or a set of other regressors, right? So this is kind of implicit in that assumption of full rank in xn prime. All right, so starting with the second and the third assumption, which again is the x's are fixed and xn prime having full rank, we can write the OLS estimator as we said, xn prime, or x prime x inverse x prime y, here using the vector notation. Now what we want to show is we want to show that this basically we want to solve the expectation of this specification of beta hat, right? So I should have just included the expectation here as well, but we'll just kind of work with this specification, and we'll simplify this a little bit and then show what happens when we take this expectation, right? So starting, and this is kind of, we follow the same step as in the bivariate case. So, you know, feel free to go back to the bivariate case video and kind of go through the steps in the scalar case and see how we kind of use the same strategies. What we're doing here is we're kind of taking assumption 1, which basically is the underlying data generating process, the linear model in the population that holds for yn, which means we can write this yn as beta prime xn plus epsilon n, right? So we're plugging in our linear model or our population model for our yn, right? That's all we're doing here, right? And then in the next step, we can multiply out this product. So we're left here with, and now we have to kind of, we're left here with xn times beta prime xn. And now I'm kind of skipping ahead a little bit, but here we're using the same transpose trick where this is a scalar, so we can take the transpose and flip around the order to get the beta on the other side. Check out the previous video where I kind of explained this in more detail to get the beta at the end here, and we have xn prime here, right? So this is kind of just this part of the product. And then we kind of separate out the sum, and we have xn epsilon n as the product right here. Okay, xn epsilon n, that's right here. Okay. Now the important thing to note is that here we have two, or we can kind of solve this product or kind of look at this. We have a sum here, and we divide, or we multiply this by this inverse, right? And we can look at those separately. If we look at the first part, we have 1 over n, n equals 1 through n, xn prime inverse times 1 over n, n equals 1 through n, sum xn prime times beta times the beta vector, right? So the important thing to note here is that this part and this part cancels out, right? So this and this is equivalent. So this cancels out, and we're left with beta with the beta vector, which is right here. And then we have the second part. We still have the sum here, and we have the second part, which is again this this chunk times this chunk, which is xn prime inverse times xn epsilon n right here. Okay, so we can isolate this beta because this part and this part cancels out, and we're left with the beta vector, right? So now if we take the expectation of this, the expectation of beta hat, we already showed that beta hat is equal to this expression. If we take the expectation of this, just take the expectation of this expression that we just derived, and now we can again kind of since we assumed that the x's are fixed, we can pull everything that is kind of constant out of the expectation, which means all we're left with is again the expectation of this epsilon n. Okay, so the x's are fixed, they can be moved outside of the expectation. The beta is the population beta that can be moved outside of the expectation. So the only thing we're left with is the expectation of epsilon n, right? So this is just moving everything outside of the expectation except for epsilon n. And then by the virtue of the fourth assumption that we made, A4, we know that the expectation of epsilon n is equal to 0, which means that this term is equal to 0, which means this entire part cancels out, which means all we're left with is our beta vector, which again shows that the expectation of beta hat is equal to the true population beta, and thus beta hat is unbiased. The OLS estimator in the multivariate case in expectation is equal to our true population parameter. All right, so this was a lot of math. There's just one last video where I go through a little bit of more math to kind of show you the underlying idea behind R squared and model fit. And then we're good to go for this week.